Now we move from theory to real aircraft case studies, where we will see how structural principles are applied to solve actual safety and reliability issues. FAA issued this Airworthiness Directive to revise the Airplane Flight Manual, AFM, to limit extended operations, ETOPS. ETOPS, Extended Range Twin-Engine Operational Performance Standards, is a certification and operational requirement that allows twin-engine aircraft to fly routes far from diversion airports, example oceans, polar regions. The core requirement is that a twin-engine airplane must be able to safely continue flight and land at a suitable airport after failure of one engine at the most critical point in the route. This is called the one-engine inoperative diversion capability. The AD temporarily restricted Boeing 787 ETOPS operations because the remaining engine could fail after a single engine shutdown, and the limits reduce engine stress until a design fix is available. AD was issued because of a structural limitation within the engine's compressor blades. It was found that certain intermediate pressure compressor, IPC, Stage 2 blades in the Rolls-Royce Trent 1000 engine could experience vibration at specific high-thrust conditions, leading to fatigue cracking and possible blade failure. During an ETOPS diversion, when one engine has already failed, the remaining engine must operate at high thrust for a prolonged period, which could accelerate this structural fatigue and cause the second engine to fail as well. Since this meant the engine's structural integrity could not be assured under required ETOPS conditions, the FAA imposed operational limits through the AD to reduce engine stress until a permanent design modification could address the blade structural weakness. This case study highlights how structural reliability and fatigue behavior influence operational limits and aircraft certification. Long-range twin-engine aircraft became viable only after major improvements in engine structural reliability, especially in rotating blades and discs. Earlier jet engines had higher failure rates, so 3 or 4 engine designs were needed for safety redundancy. As rotor integrity and fatigue life prediction improved, in-flight shutdown rates decreased, allowing ETOPS operations. This shows that aircraft configuration changes are enabled by advances in structural reliability. Engine structural life is governed mainly by fatigue and vibration rather than static strength. Compressor and turbine blades experience high cycle fatigue from vibration and low cycle fatigue from thermal and mechanical loading, and resonance can rapidly amplify stresses. Many propulsion failures arise from these dynamic effects, making fatigue and vibration the key drivers of engine structural behavior and ETOPS capability. Flight manual limits on thrust, speed, altitude, weight, or diversion time often protect structural components from damaging conditions. When structural margins are limited, operational restrictions keep loads and stresses within safe bounds without redesign. Thus, procedures and limits in operation are frequently extensions of structural capability. Aircraft certification accepts that structural failures cannot be eliminated completely, and instead requires extremely low probabilities of occurrence. ETOPS approval, for example, depends on statistical in-flight shutdown rates that reflect engine structural reliability. This probabilistic approach means certification represents quantified structural safety rather than absolute failure-free performance. Fail-safe design requires an aircraft to remain safe after a component failure, including the loss of one engine. Twin-engine aircraft must sustain loads, thrust, and thermal stresses during prolonged single-engine operation to reach a diversion airport. This shows that fail-safe principles apply to propulsion systems as well as airframe structures.